Good afternoon, everybody. Are you having a good day?
Of course.
Very good.
Yeah.
It's not raining outside, so I'm happy. So, good to see your faces again. As you've seen, we're rapidly increasing the pace of the statistical test sets we are exploring and teaching you. So, I think it's important for you to understand that it's we're applying with all these ANOVAs the same trick, and it's good to see at some point that the trick is the same, so it won't feel so different anymore. But we're really trying to give you a broad toolkit, so to equip you with all the necessary statistical tests that you would need if you set up your own, when you're going to set up your own research designs. So we're diving into the ANOVAs this block, and we're expanding rapidly. How's it going so far? The weekly assignments, it's manageable. It's maybe good to have some feedback on that. Fine, I'm reading in the chats. Also, audio feedback is always great.
Well, I haven't started yet.
For the current.
But maybe, yeah, I think it's going to be fine.
Cool. Okay. So for today, we're starting with the independent factorial ANOVA. So we have two words essentially here that are indicators. The fact that it's independent, meaning what?
That different groups belong to each condition.
Very good. And now the added part is the factorial part. And what's this, you think? Or anyone else?
Is that including a covariant?
Now we've added a covariate in the previous test, which technically could be seen as not really. No, it's not the covariate. What is it? I'm reading it in the chat.
Sorry, what was the question?
So what do you think that the factorial refers to in this ANOVA? It's an ANOVA. So it's an analysis of variance. It's independent, so it's with different groups of people, but it's also factorial. So what do you think it relates to, the term factorial? I'm getting a private message in the chat with the correct answer. Anyone?
It's probably factors, right?
Yeah, it's factors, but
I think I read something about it, but I don't know exactly.
No problem. Okay. Anyone else want to try?
Multiple predictor
categories.
Multiple categories. This is a bit. You could get confused when you're thinking about multiple categories, because it's about, and I thought you said it at the same time, you two both. It's multiple predictor variables. So the categories refer to the levels within an independent variable or a predictor variable, and the fact that it's a factorial means that it can have multiple independent variables, and each of those variables could have levels. So we're going to look into that, what that actually means. So we're going to see more of these, right? So we have we have discussed the one-way ANOVA, and the one-way referred to the fact that it only has one independent variable. So this factorial part means it has multiple. We've seen that we could do ANCOVAs, but we're going to look into the fact that we can do analysis in, so to speak, factorial way with multiple independent variables. That could also be in a more repeated setup instead of independent groups. So we're going to see that this terminology is going to be used a bit more often than just now. So it's good to have that in your mind and know what the meaning of those of the term is. Okay, so 2 or more independent variables, with 2 or more categories, but we still, and that's the thing with the whole analysis of variance, it's always with just one outcome variable, just one dependent variable. So there are also analyses that you could do which use multiple dependent variables that are actually a different measure of the same construct, but then you're going into the realm of MANOVAs, which stands for multiple analysis of variance, of course. But we're sticking with ANOVA, so it's just one dependent variable. This is restating what we just concluded, but it's good to have a clear understanding of this. And I think I also, I'm not sure if I mentioned this at one point. It's also good to try to visualize such analysis in the way the data is structured in SPSS. So for example, if I'm thinking of this independent factorial ANOVA, I know that in SPSS I have a column which stands for one independent variable which could have 2 or more categories, and I have another one because it's factorial which also has categories. I could have even more, but I'm sticking to 2. And we have a column for the dependent variable which actually contain the scores of the thing that I actually want to measure. So it's good to try to visualize what these different kinds of tests, how the data is represented for these different kinds of tests, just to give you a sharper notion of which test actually performs what. Okay, so in terms of assumptions, it's all very close to what we've been doing so far. We want to test on a continuous variable, the dependent variable. It has the samples that you would take need to be random, and we've talked about this earlier, that random actually means random. So if you're restricting your research, your design, your experiment to only include psychology students, well, then it's not actually really a random sample. You could do inferential statistics, of course, but you have to realize that you only are generalizing to that specific group then. So you have to be, if you want to be strict, you have to do a really random sample across the entire population if you want to generalize to that. The same holds for the normality and the equality of variance, where we just apply the same tricks that we did with t-test. So this is nothing actually new here at this point. Okay, hang on to your hats, because when we're talking about analysis of variance and what we've seen in the previous lectures on when we only did the one-way ANOVA, we've seen that we can decompose the different parts of the variance into an explained part and an unexplained part. And what's happening with the factorial ANOVA is that we're actually adding more variables to our model. We're adding independent variables, and in this case, let's see. Well, in this case, I'm adding 2 independent variables to the models, and it's called the independent variable A and B. I just term it in generalized terms here, so you can so you have a general way of understanding this. But the one thing that is added, and that is something that differs from what we've done with the ANCOVA, is that we also add to the model an interaction term. And we've talked about this interaction before, where in the ANOVA yesterday, we wanted to test if there was an interaction between the covariate and the independent variable. And within the ANOVA, it was an assumption that there should be no interaction between these two. Because if there is, then the interaction explains parts of the results, and well, then you can't correct for that covariate. But here, what we actually want to know if there is an interaction going on. So we want to determine if there's a main effect of A or a main effect of B and what they do together. And so I'm not sure if I mentioned this before. Did I mention the example with the pills that make you healthy? I'm not sure, because I'm giving multiple courses at this. So. You don't think so? Okay. So I'll do it again, and if I already stated it, then it's just reiterating. But for example, you have pill A, and it makes you better. And you have pill B, and it also makes you better. And if you would take them both, if you were to get better, even better then, because you combine the two, that would be an example of no interaction. So the effect of pill A is that it makes you, it increases your health, and the effect of pill B also increases your health. And if you take them both, well, it just adds up. So there's no interaction going on. But if you take pill 1 and you get healthy, and you take pill 2 and you get healthy, but if you take them both, you die, that's an interaction. Because combining those two variables does something else to the end result. And that is what we're interested in to find out.
Is it like plus and plus is positive and minus is also positive?
No, not. Maybe it's clear. So, for example, some experimental design could have a positive effect. For example, you have an intervention and it increases your emotional stability, for example. If that is a general result, then that should hold for everyone. And if you do an analysis where you also split up for gender, for males and females, and the treatment works in the same way for men and women, then there's nothing going on. But if the treatment increases the emotional stability of females, but it decreases the emotional stability of males, then you're talking about an interaction. So it's the effect of something that you want to measure. Does it work in the same way on different levels of some other independent variable, for example, gender? Does that make sense?
Yeah.
Okay, very good. So when you want to decompose these variance components, we're again trying to see what the amount of variance there is to explain. So that just means looking at the dependent variable, determining what the mean is of that dependent variable, and seeing what the differences are for each individual score to that to the total mean. And then we can see, can we decompose these two parts? And that is what's going on with the Factorial ANOVA, is that it adds it has a model which is expanded upon, where you with a one-way ANOVA you just have one independent variable. Now you have two, and you add an interaction term. So the model contains essentially three parts: the separate part for each individual independent variable, and the interaction between these two, which actually is just a multiplication of those two. And what this does, essentially in the same way as we discussed yesterday, because we add more explanatory variables to the model, it decreases the amount of error that we find in our model. So what you're going to see shortly is that the error term that we have here is going to be reduced, but the same error term, which is defined as the mean squares of the error divided by the mean by the degrees of freedom. These mean squares of the errors are the thing that actually are used everywhere. So for every piece of the puzzle that we are going to look at today, we should realize that because we are adding more explanatory variables, we decrease the error term, and that reduction in error essentially makes for having a higher signal to noise ratio, and that is how the error term is used in this analysis. It looks a bit daunting, this sheet, but we'll go through every step and look at each and every piece of the puzzle, and I hope by the end of this lecture you have a thorough understanding of what is actually going on here. So let's first look at the example that we're going to use. We're going to measure the amount of accidents in a driving simulator. We're going to put people in a driving simulator a few times. We're going to measure their average number of accidents that they have. And we're going to do an experiment where one group gets no speed and gets no alcohol. The other group is given a bit of speed and no alcohol. And we're going to create experimental conditions for each and every combination of levels of speed and levels of alcohol. So that means that the total amount of permutations are 9, because you could be someone in the 0 alcohol, 0 speed condition of the alcohol condition 1 and speed condition 1, which has which is no speed. You could have no alcohol, a bit of speed, no alcohol, a lot of speed, up until a lot of speed and a lot of alcohol. And well, I've just filled in some scores here that could be possible outcome variables, but this is the way it is set up. And the data looks then a bit like this. I have alcohol, which could be none, some, or much, and we have the amount of speed, none, some, or much. Yeah, here we have it. So that means that we, in this, for this example, we're going to have 2 independent variables, and we have 1 dependent variable. It's the average number of accidents, which are shown in this column, and we're going to use those for our analysis. You also see gender, so that means that we could actually expand our model with also looking at the difference between males and females, and if we would like, we could even do a independent factorial ANOVA, but we're not going there. But it's good to see that, and to because we're not covering each and there are even more options in statistical analysis that you could do. But seeing this, it could also trigger you to see, well, oh, if I'm doing a factorial ANOVA, I could also throw in a covariate of 1 or more. It's all possible. So this is the way the data is structured and what we're looking at. Is that clear?
Yes.
Very good. So we're first going to look at the sums of squares of the model. Of course, we have the total amount of variation that there is, which I told you about. It's again looking at the difference between the total mean, and in this case, that would be the average number of accidents. So the total amount of variation that there is the deviation of each and every score for each individual with the average of this entire column. and squaring those differences, adding those all up, will land us the total sums of squares. So if you know that, you know the total amount of units that you can actually explain. But for the model part, we're looking at the part that is explained by the entire model. And the thing that I mean with an entire model is the model where you have the two independent variables, speed and the alcohol, and the interaction term. So if I have those three in the model and I want to predict the outcome, then I will get some results here that actually are the predicted variables. No, let's state it differently. That actually are the predicted values for each individual. And what you're going to see is that those values are, because we're combining categorical groups, those are actually the means within the combined groups. So if I look at the averages for within each group, so I have the group a lot of alcohol and a lot of speech, much, then the average score is 7.5. And so here I have all the means for each and every one in the group. So that means that if I want to look at the explained part for the entire model, I have to look at the difference between, and this is in the same line of reasoning that we had with the one-way ANOVA, where we said we have men and we have women and we're looking at their heights, and if you're part of that group, your expected score is the average of that group. So this means that the group mean for everybody that is in the no speed, no alcohol group, so those are all these people up until, still going, up until here. Now we're changing the amount of speed that is consumed. But the average is all the same for these people. So if we want to know the explained part here, we're looking at the difference of the grand mean, and with the grand mean we mean the mean of the amount of accidents for everyone, the difference between that and the group mean, and with the group mean we mean this specific group. So it's the difference between these two that actually indicates the part that is explained within this entire model. So they are all the same. So even without looking at the formula, you could realize that if you're looking at these distances, and if you subtract these and square these, then you obviously have to multiply it with all the people that are actually in this group, because it's the same for this one and that one and up until, let's see, up until here. It's all the same, so you have to add those up. And if we do, so if we add up all the differences scores, let's see, we have the mean of everyone. I'm applying a subset, so everybody that is in the no speed condition, everybody that is in the no alcohol condition. What is the mean amount of accidents for that group? So I'm defining a new variable, which is m from mean for K1, and with K1 we are referring to the first group. We have 9 groups, so we do that for all 9 groups, and then we have all the averages for these people. Does that make sense?
Yes.
Very good. We also need the number of people within each category, and in this case it's the same, but it could differ per category. It's not necessary. You don't have to have equal groups. So if I want to calculate the sums of squares for the model, then I have to look at, well, what's the difference between the group mean, everybody in group 1, and what is the difference of that with the total mean. So it's the mean of all the accidents. I have to square those distances, because if you don't square them, they add up to 0. And we have a lot of people in that group, so I think it's about 20, so we have to multiply that distance with the number of people in that group. So the sums of squares for group 1 is equal to the squared distance times everyone that is in that group. So if you want to know the total number of the total sums of squares, we just add all these sums of squares for each group together, and we will find total sums of squares of 494.2205. Well, again, just as I stated in previous lectures, this is quite abstract, so it's always good to try to visualize the thing that we're looking at. So visually, it's the same as we've seen with the height. We're just looking at all these people. So what I've done here is put all the participants on the x-axis, and the score on the dependent variable on the y-axis, and each individual score you can find in the black circles. That's the score for each individual. And the deviation for each individual with the total mean is indicated by the black line, and it starts here and it goes down to here. And what I've also done is added the average within this specific group that the person is in. So this one is obviously in the no alcohol, no speed group, and I put the average in red circles here for the group. So these are 20 people all in the same group, and these are 20 people all in a different group, no alcohol, a bit of speed, I think, and so forth, up until we have the final group that has a lot of alcohol and a lot of speed. So the formula that you are provided, so I have to go up for the formula for this one. It states we're going to sum the difference between the group mean and the total mean squared multiplied by each individual that we have in that group. And we're going to do the sum refers to we're summing over each and every group that we have. So it's just stating, look at the difference between group mean and total mean, square that distance, and add it to the next one. Or what it's actually stating is, look at the difference between those two, multiply that with all the people in here, those are 20, and then you got your sums of squares for the first group. And sum that over, well, the next group, and the next, and the next, until you have all the groups. And that will land you the total amount of explained variance that you have in there. Does that make sense?
Yeah, I have a question actually.
Of course, no problem.
So the red line, is that the group mean, if I understand correctly? So where it's written like full model, and then the red line basically.
Yeah. So, and you can be a bit more explicit about what you mean with the red line, because we have red lines going up.
Oh yes, right.
And we have circles going there. So the group means are the red circles horizontally. Yes. And the lines going up, so the vertical lines, that is essentially the difference between these two, between the group mean and the total mean. So that's correct what you're saying.
Okay, thank you.
Yeah, very good. So this is the amount of explained variance that you find in your model. So if we look at the error term, again, it...
Sorry, can I ask one more question on this?
Yeah, go ahead.
So why do you calculate a mean for each group individually instead of just looking at the difference per participant in that group to the ground mean? Isn't that the same?
Could you repeat that one more time?
So right now you're looking at a group mean first, and then
Yeah.
you're taking the difference between the group mean and the ground mean, right?
Yeah.
And then squaring that.
Yeah.
But you could also just take the difference per participant from each group and take the ground mean of that and then square it. Isn't that the same? Because it's the mean of each group. So you like, I don't.
Yes,
really
no, but what you're saying is, so if I understand correctly, and I'm not sure, you're saying, can't you look at the group mean and look at the difference between the individual and square that?
No, I was saying, can't you look at the difference between the individual and the ground mean? Isn't that the same as taking the group mean and then?
No, it's not, because if I understand you correctly, because if you're just looking at the individual, for example, this one,
Yeah.
and I'm looking at the difference between this score and the total mean, this is not the part that is explained. It's just the amount of variation that you have. The thing that you could do, though, is instead of summing over each group and then summing over the next group, you could also say, well, if I know the distance for each individual of this group mean to the actual score, you could just sum over everything. That would yield the same results.
Right.
But if I'm sticking with the formulas that Field provides in this sense, so
I just didn't really see the benefit of using the group means. Like at the end, it's just the sum of squares, right? I don't really see the difference between.
No, you need the group means to determine the sums of squares. So the part that is explained is the fact that you're part of this group. That is the explaining part, and the fact that you're summing those squares is the difference between that group mean and the total mean of the total of all the groups together. So
Right.
you really need that piece of information to determine which part is the explained part, and conversely, you also need that information to determine, well, if that is the explained part, then what is the unexplained part? And you also need that information for this. So you need to look at the variance components for the unexplained part in the error that we have here. So we'll look into that, and if it's still not clear at the end, come back to that. So for the error, this is a bit again, as I stated earlier in earlier lectures, putting the variance here is a bit misleading, because it's not clear what's going on here. You say, well, we're multiplying the variance with n-1, but the variance in itself is the sums of squares divided by n-1. So if we multiply it again with n-1, we're obviously stuck at this. We get back at the sums of squares. It's the same as saying 6 divided by 3 multiplied by 3. So it's still 6. So, but what it's actually stating here, and I'm using this formula because Field is also doing that. Is actually, what is the sums of squares? What are the distances between the actual score and the mean within the group where the individual is put into? So I'm simply using the variance function in R to determine the variance within the first group. And I'm multiplying that by the degrees of freedom for that group. So that is the number of people in that group minus 1. And that results in the sums of squares for the first group, for the second group, for the third group, up until the 9th group. And if I want to sum the squares of all those different groups, I just add them all together here with the sum function, which results in sums of squares for the error of 66.34 and a bit. Visually, this is also clear, right? If you have an explained part of the model, you also have an unexplained part. So if the explained part is the part from going from the total mean that you have to the mean within the group, then the unexplained part is then what's left. It's called the residual, it's called the error, it's called the unexplained variance. And that is for this individual, it's how much you're off with your expected score based on your complete model. So it's the deviation from the score of the individual with the group mean where that individual is from. And for this one, it's, well, you have an explained part and then an unexplained part, but it could happen that you overestimate, for example, the expected outcome because the group mean is higher than the score of the individual actually is. So that means that you have an explained part that runs from the total mean to the group mean, and then an unexplained part that goes back again to the actual score of the individual. So in this case, you would have more explained variance than you have unexplained variance. Does that make sense?
Yes.
Yeah.
It's still
Maybe
purple.
Sorry,
Yeah.
could you maybe show the part where it's still unexplained? I didn't get that.
So the unexplained part is the deviation from the individual score, the black circle here that I'm pointing at, to the group mean. And the group mean is indicated by these red circles. That is the unexplained part. In other words, the purple vertical lines, those represent the unexplained part here. Yes?
Yeah, thank you.
Sorry, I'm sorry again. So I'm just curious if the error is the part that is basically the distance between the subject and the group mean.
Mm-hmm.
How could the error ever be higher than the explained variance? Because the group mean is always closer to the individuals of that group than the total mean would be, wouldn't it?
It doesn't have to, because if these scores, for example, the scores of the people within this group are very close to the group mean, and they could be spread out further. So it could be that this score would be up here, and this score would be up there, and this score would be down there. So you could have a lot of unexplained variance in that sense.
Yeah, I see. Thanks.
Yeah. Okay. So we've now looked at the explained variance. We have looked at the unexplained variance, but we're not there yet now, because we now know how much variance there is in the model that is explained within the model. And we now have our unexplained variance component. But we also want information. We want to know if there is a main effect for both the independent variables, and we want to decompose also the interaction part. So we have a model with two independent variables and an interaction. If we want to say something about the individual independent variables, if we want to say state something about the main effect of speed or the main effect of alcohol, we have to look at those components. So having the knowledge of how much variance there is in the model where we combine everything, and having the knowledge of how much is then still unexplained, we could now look at how much is explained by if we only aggregate over one of the independent variables. So what is done here is when we're looking at speed, the way it is set up is essentially the same as we've seen with the previous example. so what is stated here is we are again looking at the mean of the group, and we're subtracting the total mean, we're squaring it, and we're multiplying this with all the people in that group. Only the definition of the group is now varying, because what we're saying is then that if we're only looking at the people that are in the speed group, we're neglecting the fact that there are people in there that are in the no alcohol, a bit of alcohol, and the much alcohol conditions. So we're actually, instead of splitting things up into 9 separate groups, we're now splitting things up into 3 groups, only the no speed, the little speed, and the much speed conditions. So we're aggregating over 3 groups, and we're neglecting the information that is in there about the subject within that group being part of a specific combination of levels of alcohol. Does that make sense?
Yeah.
Okay, very good. So what we're doing here is, again, we are calculating the mean. So the mean for the first one, and I'm selecting the subset where only speed is none. So we're neglecting the fact that someone is part of an alcohol condition. We're just saying, well, it's speed. So we're having the none, the some, and the much conditions. And we had 20 people within each subgroup. So if we're combining 3, we're now at 60 people within the groups. And that holds for the first one, for the second one, and for the third one. So calculating the sums of squares, it's the same trick again. We're looking at the mean within this group, so the mean where we combine everything and only look at the no speed condition. We look at the difference of that mean with the total mean again, squaring this and multiplying it with all the people that are in there. And we're doing that same trick with the a little speed and much speed condition, both. All 3. So that will result in 3 parts of the sums of squares. We add those all together, and that will result in the sums of squares for speed, which is 128 we find here. Again, we want to look at this visually because it gives us a little bit more clearer view of what's going on. So what we're seeing here is actually, well, let's have a closer look here. We have the speed, the 3 different conditions of speed, and I still left in the expected model outcome. So if we're looking at this one, we see the 3 groups, but they're a little bit spread out because just the way the data is ordered, we ordered the data in this way. We will see with the alcohol condition that the ordering is a bit different, but everyone in the no speed condition are these people together with these and together with these. So now we're averaging out over this group, and the averages are found by the green circles. So the average within the no speed group is here. It continues still the same and still the same. And when we're talking about the deviation from the total mean, or the explained part of this particular model, of the explained part of this particular independent variable, we're looking at the difference between the total mean and the mean again within this group. So we're squaring that, multiplying this by 20 people here, another 20 here, and another 20 here. So that's 60 people, and the differences, the squared differences are all the same for each and every one in this group. So we just multiply that distance by 60. And we also do that the same for everyone that's in the little bit of speed condition. So those are these people, and these 20, and these 20. And finally, the same thing for the high speed condition. These 20 people, this one and this one. And the total sums of squares that is explained by this independent variable is the green vertical, all these green vertical lines squared, all added together, and that will result in how much explained variance there is for this particular independent variable. Are you still following me?
Yes.
Very good. Now the same holds for the other variable, because if we look at speed, we want to know the main effect of speed. We also want to know the main effect of alcohol. So we're applying the same trick again. We're saying, well, what is the mean of everyone in the alcohol conditions? Either no alcohol, a little bit of alcohol, or much alcohol, disregarding the conditions of speed that people are in. So again, we then have 60 people. We're looking at the distance between these two means. We're squaring them again and multiplying with all the people in this group. And we have 3 of them, so we're adding those sums of squares for the non-group a little bit and the high group. So here I'm calculating exactly in the same way the means for those two groups. I'm determining what the sample size is for each and every one. It's 60. And then calculating the sums of squares, multiplying the number of people with the squared distance between the group mean and the total mean squared. For the sum of squares of all 3 groups, add all those together by the sum function, and that results in the total sums of squares for alcohol of 364. Again, visually. And the ordering is a little bit nicer here, because we have all the people that are in the no alcohol condition in the front, and all the people within the little bit of alcohol condition in the middle, and the high alcohol condition to the right. So we again see the group mean. So for all these people, the average is here. The difference is indicated by the orange vertical line. We square that, multiply it with all the people that are in there. Those are 60. And we do the same thing for a little bit of alcohol condition. And we do the same thing for the lots of alcohol condition. Add all those squares together, and that will land you finally at the amount of sums of squares that we have for the alcohol condition. Does that make sense? Up until now? Yeah? Okay. Then, I suggest before we dive into the interaction that we go get a cup of coffee, and then we're fresh and sharp when we get back. Is that okay with you?
Sure.
Yeah. Very good.
Yes. Yeah.
We're starting at 2 o'clock. So here we go again. Well, the good thing from teaching at home is that I actually have coffee, because when I'm in the lecture hall, I also say that, let's go get a cup of coffee, but then there are always a lot of questions in the break, so I can't even drink coffee when I'm in the lecture hall. But now I can just go and get some coffee. So, we were going to discuss the interaction term. So let's go into this. So what we've seen up until now is that when we're looking at the total amount of variance that can be explained in the model, and we've defined that by having the expected values of the entire model, which are actually the in this case, in our Factorial ANOVA case, the means for each individual group that there is. You can imagine that if the sum of the parts is the total, then that would mean that the sum of the parts actually explains the entire thing. And so when looking at the interaction term, or at least determining if the interaction does something else than the sum of its parts, if that differs, if the sum of the parts differ than what is explained by the entire model, or at least if there's something left, then that is an indication that the combination of the two independent variables are actually doing something else than you would expect. So if you look at the way that the interaction term is defined here, so we're looking at the sums of squares of a times b. It's defined as essentially subtracting the sums of squares from one independent variable and the sums of squares of the other independent variable from what is explained by the entire model. So if there's no interaction going on, then the sum of the explained parts, the sum of the sums of squares of the two independent variable would be the same as the entire model. So if we're looking at this, we have these distances for one independent variable, all the orange vertical lines, and for the other one, we have all these lines, the green vertical lines. So if we would add those two, and it would be the same as the expected values for the total model, then there would not be an interaction. So if you add those two and there's something left, then we're talking about interaction. So in this case, we have to we actually calculated all the parts already. So we're looking at the sums of squares for one model and the sums of squares for the other. Go ahead.
So that means that if there's an interaction effect, SSAB would be something else than 0. And if not, then it would be 0, right? Because it's like SSA and SSB is the same as the SS model, then
exactly.
The whole thing would be 0. Yeah.
Exactly, yeah. So so if you look at the way Field states this formula, he states that you subtract from the model the sums of squares from group A for independent variable A and the sums of squares for independent variable group B, so these two. But you could also say, well, add group independent variable A and B and subtract them both from the model. So it's stating the same thing, of course. But you're absolutely right that if you subtract the things that you explain with the total model from the combined two independent variables, and there is no interaction, then you would end up at 0. But if there is, then that is the part of the explained variance that we attribute to the interaction going on. And so to calculate these two, well, that's not really a hard part. So we only need the sums of squares of the model, which we already calculated. We need the sums of squares of speed and the sums of squares of alcohol, and subtract this from each other. And then we're left with the sums of squares for the interaction between speed and alcohol. And we see that the sums of squares is 1.9. Do you think that this is a significant sums of square? Anyone? Do you think, based on this result, that there is actually an interaction going on?
Well, it depends on the total variance, and I forgot what that
Okay,
was.
that's a good observation. So I think earlier on we determined that we have about 400 something points of total variance.
Okay, in this case, I would say no.
Exactly. I would absolutely agree. And you could also see it a bit, right? If you look, so the total model, the expected scores for the total model are the red circles, the red horizontal circles here, and the orange circles are the ones for one independent variable, and the green ones are those for the other independent variable. So even just eyeballing this and looking at the greens, if I add the greens with the oranges, well, I'm about at the same point as the red circles, right? I think that this one would be a bit overestimated if I also add the green ones to this, but this one would be, I think, spot on. Yeah, so I wouldn't assume that there's much variance left even eyeballing this, but actually calculating this will yield us 1.9 variance units on a total variance that is more than 400. So this is nothing. But we will actually test this, of course, because, hey, that's what we do.
I'm sorry. Could you repeat the results, please? I did not understand what nothing means. That doesn't mean nothing, so.
What nothing means? What do you mean with nothing?
Yeah, the total variance of 400 something, and then the.
Yeah. So okay.
0.9.
I can go back, but it's way up there. Oh, here it is. We saw that the total amount of variance that there is to explain, so the distances between the total average for the number of accidents and each and every score was 400. It's almost close to 500. It's 494. So if only 1.9 parts of these are attributed to the interaction, well, that's not much, right?
No.
That's not explaining a lot. That's what that meant.
And then, therefore, the conclusion was that these two independent variables have an effect on each other.
So we're not at the conclusion yet. I expect that they don't, but we still have to test it. So if we have the sums of squares for the interaction term of 1.9, then, well, I need to test this. So when you're doing an independent factorial ANOVA, you will get a few results that you could be interested in. First, of course, you want to know if there is a main effect of the independent variables on their own. So essentially, what is the effect of speed? What is the signal to noise ratio for the speed condition? And what is the signal to noise ratio of the alcohol condition? And finally, we want to know if there is an interaction going on. So the speed times alcohol, the alcohol times speed, the interaction term is also, we also create a signal to noise ratio for that one. And of course we use the sums of squares, the sums of squares of 1.9 that we found already, to calculate the mean squares by dividing by the degrees of freedom, and for each and every one using the same mean squares for the error. So in the beginning of this lecture I already stated that by combining all these variables into the total model, then the thing that is unexplained is what's left after we added the total model, where everything is put in, all the independent variables and all the interactions. And we use that same error term to determine the F ratio for the independent variables and also for the interaction. So the error term here is always the same. So we're gonna apply that. So what do we need? We need the sample size. We need to know the group size for speed and for alcohol. So that's 3. We need to know the group size for the model, and that was 9 because we have 9 groups, right? And that also means that based on those values we can determine the degrees of freedom, which are given in the formula, the formulas in one of the first sheets. We need the degrees of freedom for speed and for alcohol. Well, that was the number of groups in the speed condition -1 and the number of groups in the alcohol condition -1, and the degrees of freedom for the interaction of speed with alcohol is the degrees of freedom for speed multiplied by the degrees of freedom for alcohol, and that is equal to 9, of course. No, sorry, I'm not saying that correctly. What's this supposed to be? Anyone?
4.
Yeah, because it's 3 minus 1, that's 2. This one is also 3 minus 1, that's 2, so 2 times 2 is 4. Yeah. So now we have all the parts. So if I want to look at, if I want to calculate the mean squares for the interaction term, I divide the sums of squares for the interaction by the degrees of freedom for the interaction, and that will result in the mean squares for that interaction. And if I want to determine the mean squares for the error, I have to divide the mean squares, the sums of squares of the error by the degrees of freedom for the error, and then I have the 2 terms I need to create a signal to noise ratio for determining my f value. So my f value here is dividing the mean squares for speed and alcohol interaction by the degrees of freedom, which is 1.2. So this 1.2 is the f value, so the signal to noise ratio. And we already eyeballed the sums of squares of 1.9, where we thought, well, that's not a lot. So do you think that this f value is significant?
No.
No.
No, of course not, right? And because you know the f value, the higher it is, the more signal to noise there is, but it's also good to understand that if it's a signal to noise ratio, then if there's as much signal as there is noise, then you end up with a ratio of 1, right? So that already makes clear that if it's close to 1, then there's probably nothing going on. But we're going to test it anyway. So we're applying the visualize function for the f test, and that will result in the null distribution for the f value for this specific experiment, meaning having 4 degrees of freedom and for the model, and having 171 degrees of freedom for the error. And that results in this null distribution, where we find our found test statistic to be here at 1.2. And we see the probability of finding such a test statistic or more extreme underneath the null distribution up until this point. So it's the blue area. And that area, that probability, is equal to 0.299, which is higher than our 5% that we could choose for our alpha level or for our type 1 error, which means that, what does this mean?
It's not significant.
It's not significant, and in terms of what we're looking at, it means that there's no significant interaction going on, because we were calculating the f value for the interaction term. So we're concluding there's no significant interaction. Does that make sense?
Yes.
Yeah.
Very good.
So basically, the speed and the alcohol increase the amount of accidents separately.
Yes. And the combination of both doesn't show any different results. But we will be looking at this. We're going to run the same analysis in SPSS, and we're going to look at what the results are that they provide, and we're going to check what we've calculated, because the reason we're doing this whole exercise is, of course, first for you to have a thorough understanding of well, what we're talking about when we're analyzing variance, but it's also to take away the black box of SPSS, because there are some SPSS books even that only tell you which buttons to push and where to look in which output and what to conclude. But hey, our course is called Scientific and Statistical Reasoning, and we want to find the dragons. So we're diving in to make sure that you understand what you're what's going on behind the scenes in SPSS. So before we do that, was there another question?
Yeah, just so if you put it in words, it would mean there is no difference in number of accidents between the groups who took alcohol and speed and the group who only took alcohol or only took speed.
The combination doesn't lead to different results.
Good,
and
good. Okay.
And of course it's hard to verbalize when you're only looking at these significance levels. But when we run the analysis in SPSS, we're going to create we're going to run the analysis there, and we are also going to create a plot for those results to see where the differences are actually. And then if you see what's going on, it's easier to verbalize the results of your research. So we'll be doing this also. But before we go into this, to that, just a little bit of this. Here I've plotted the same results. The null distribution of the F and our alternative distribution. And this is an arbitrary alternative distribution, one that I made up, an alternative distribution where something might be going on, actually. So my question to you is, if you look at these plots, and so we're getting back to the Neyman Pearson null hypothesis testing again, what are the areas that we are looking at here? And it's not about me getting an answer, it's about you thinking if you know the answer to the question that I'm asking. And if you don't, try to write it down and try to find out at a later point or something. But let's hear it.
We have the critical value and the p-value. We can see here that the p-value is exceeding the critical value. So we can conclude that it's not significant.
Mm-hmm.
And we can also see the alpha and the power.
Okay. So that's exactly what we're seeing. Very good. But my question would also be, in terms of exam questions, I want you to point out which one is one then. Which one is what then? Anyone else? Or you may answer for if you wish, but you can go ahead.
So the green one is the power.
Yeah. And where does it go from?
It's from the critical value below
the
alternative hypotheses.
Yeah. So it's the fact that our critical value is here is because we chose an alpha of 5%, and this 5% is shown under the null distribution, and the area under the null distribution of that 5% stops here, exactly at the critical value. So our power starts at the critical value, it goes up to this point, and it's the probability under the alternative distribution. So it's this all the green areas, starting at the bottom here, right? Because I've heard students sometimes talk about the area stacking on top of each other, but that's not the case. It starts here at the bottom. It's the area under this curve, and that goes down all the way to here. And what? How would anyone else define this power again? It's the probability of what?
It's the probability that we determine that there's an effect when there actually is an effect.
You're going in the right direction, but there actually is an effect. Could be a bit more specific. So, because essentially you're always saying to the right side of this, you decide to determine that there's an effect. And if you're only looking at the null distribution, you're concerned with alpha. But now we're looking at the alternative distribution. So if we would decide to determine that there is an effect, what is the probability that there actually is this effect of this specific alternative distribution? So your answer is, in fact, it's a good answer, but it should be related to this specific alternative distribution, because only for this specific alternative distribution you could know what the actual power is. Or maybe if you do meta-analysis and you have a lot of information about the mu of the alternative distribution, you could find it. But it's good to know that it's related to the other distribution. Very good. So where do we find the alpha? Anyone else?
It's the red smaller area.
Very good. So it's the smaller area. It's the area, to be more specific again, the area under the null distribution, the null curve. And it starts, it's the 5%. Well, I haven't made it explicit that it's 5%, but it's the red area, and we already stated that the critical area is here. And the blue area, what do we call that again?
The p-value.
Very good. And this point on the y-axis?
That's the test statistic that we found.
Very good. I think you're there. Good. That makes me so happy.
Is the green part is power, or is that beta? Because I get confused between the two.
It's the power.
Okay.
So beta is also under the alternative distribution, but it's on the other side.
Oh,
so,
okay.
So the power is the power is associated to the conclusion you take. So if you decide the conclusion is to reject the null, it's also the power that's on that side.
Okay.
Yeah?
Yeah, thank you.
Okay. So let's look at this in SPSS, because we're well, we've seen how to calculate all these parts, but it's also good to see what it's like when running the analysis in SPSS. And so what I want to suggest is that you run me through running this analysis in SPSS. So what do I have to do? And you have to tell me. Where do I go?
To analyze, probably.
Yeah, that's a good start. Very good. And now?
It should be under compare means.
Okay. Everybody agrees?
No,
No? What do you think?
I don't know.
You don't know, but you don't think it's under the compare means.
Yeah,
Anyone else?
Linear model.
General linear model. Yes, that's right. You do have the ANOVA under general linear under compare means, but this is the one-way ANOVA, right? And now we're looking at the factorial ANOVA, so we shift our attention to the general linear model, and we are stuck with the univariate. So that means we're looking at analysis with only one dependent variable. So if we do that, then this shows up. What goes where? Tell me.
Accidents go in the dependent variable.
That's right. So our experiment was about the amount of accidents that we have. And now what?
Alcohol and speed go into fixed factors.
Yeah, they both go into fixed factors. That's correct. Because we're looking at both these terms. We want to know the main effect for both, and when we run this full factorial model, it will automatically add the interaction term in here. So that's very good. Now, we could stop there, but as we've already stated with our one-way ANOVA, if there are more than two levels within our independent variables, and we find an effect, we find an ANOVA which states that there is a more signal to noise for one of the independent variables, then we don't know where that difference is. Is it between no speed and a little speed, or is it between no speed and much speed, or is there only a difference between much speed and a little speed? So we have to find out where these differences are. And as we've discussed earlier, you can do two things. Either you could have hypotheses about these differences where you could run your contrasts, and where you had to manually fill in your contrast with the one-way ANOVA. The factorial ANOVA just provides you with a few options. So you have the ability to choose a specific kind of contrast. I think I've already stated for this course that I won't be asking you to know the differences in all these contrasts that will be provided. I have stated before that it's the Helmert contrast is the one that is technically the best, in the sense that it respects the amount of variance that there is to explain. But as we've seen, I think yesterday also, that it doesn't always give an answer to the specific questions that you have. So I'm going to do the Helmert contrast for alcohol, and I must remember to change this, because otherwise it will stay at none here and then nothing will happen. But for speed, I'm going to choose the simple contrast. And when I do the simple contrast, I can determine what the reference category is. And it can either be last or first. And the last or first refers to the numbering that you have applied to your independent variable. So if your first is 1 and your second is 2 and your third is 3, then the last is 3. So what should be our reference category in this one for the independent variable speed? Last or first?
First, maybe.
First.
Ooh, that's echo. Could you repeat that?
Maybe the first one.
The first one, why?
Because it's the low speed and you can compare it to the other two.
Yeah, it wasn't the low speed, right? It was the none speed. So we had no speed, a little speed, or much speed. But you're absolutely right that the lowest category was for the first one. So I'm going to compare it to the first one. Change that, and that means that the little speed, a little speed will be compared to no speed, and a lot of speed, much speed, will be also compared to no speed at all. So that is what the simple contrast is doing.
How do we, can I ask a question?
Go ahead.
How do we know which test we're going to choose or use? And also, I don't really understand this first and last thing.
So it's determining which group you are comparing. So where your ANOVA or factorial ANOVA in this case just states, well, there is an effect of speed. Now we want to know, well, which one differs from which one? Is it the no speed that differs from a lot of speed, or a little bit of speed? So we want to know where the differences are, and that's what the contrasts are providing us.
No speed is the first, but then you can't choose middle speed.
No, so what's it stating, the simple contrast? It's stating that we will compare all other categories to this baseline category.
Including the category you select.
Yeah. And we'll
So
see
you're
the results.
comparing-
We'll see the results in a second. So we can see what is actually being compared within these contrasts, which will probably make it a bit more clear, I hope. Yeah?
Sorry, there's a question in the chat asking when do we have to choose simple and when do we have to choose Helmert contrasts?
Yeah. So it depends on the research design that you have and the hypothesis that you actually have to get some answers on this. So if you want to, for example, if you want to know the difference, if your hypothesis is that speed, a lot of speed causes more accidents than a little bit of speed, then you're comparing these two. And to get an answer on that question, you could use a Helmert contrast, because you could say, well, do the combined groups differ from no speed? And then if we split it up, do these two differ? But if your hypothesis is, well, I think that that a little bit of speed increases the amount of accidents compared to no speed at all, but a lot of speed increases that amount more, well, then your hypothesis is about the difference between no speed and a little speed and no speed and a lot of speed. So then your hypothesis actually doesn't allow for a Helmert contrast because it doesn't give you an answer to the question that you have. So it's very much dependent on the hypothesis that you're stating. And yeah, that's it.
Okay, thank you.
Yeah. So I understand also where this question comes also, of course, a little bit from, well, if I have the exam and I have a question and I do a contrast, do I have the good one, the right one or not? But I will not ask you these kinds of questions. If I want to know if you're able to perform or interpret a Helmert contrast, I'll show you a Helmert contrast and I'll ask you to interpret this. So, yeah. Okay. So we have the contrasts. The plot, let's see, should we make a plot? What do we need to do if we want to make a plot? Here?
We can't see the slides.
Oh, sorry. Here you go. So I can have a horizontal axis and separate lines. And it actually doesn't really matter which you put where, right? So what I can do is I can put the alcohol on the horizontal axis and the speed on separate lines, and I could add these. You could choose for a line chart or a bar chart, and even include the error bars if you want to. And the results from this one are what? What do you think this is? What kind of graph this will produce? Anyone?
A graph showing the scores of speed under the variable alcohol.
Yeah. So essentially, it's the interaction. It's visualizing the means of the interaction and visualizing the error bars only for the interaction. So we've already determined by calculating it ourselves that there actually is no interaction going on, but it will be good to see what's actually going on, what it looks like. But it also means that if you want to interpret the main effect visually, that you could also add those charts for just the main effect. So if I add the speed and alcohol separately, it will produce new charts, one with only for speed and one only for alcohol. So now we have 3, including the interaction. Okay. And what will we do next? Well, if we don't have hypothesis and we just want to explore, well, then we can do multiple comparisons. We can do the post hoc test on the speed and the alcohol, and we could, for example, choose a Bonferroni as a post hoc test, or a Chuki. Again, we have a lot of post hoc tests here, and you don't have to know the differences between all these types of post hoc tests within this course. So there are, of course, there are differences, and you could dive into the technicalities of these differences, but the preferences of these post hoc tests, or well, also in general for certain kinds of analysis, are also related to the journal that you're writing for. So some journals absolutely swear by doing one of these, for example, the Scheffer contrast. So, well, if the journal wants the Scheffer contrast, then we'll be doing the Scheffer contrast. That's also a practicality that comes into consideration here. So I chose 2 for now, and I think I'll leave it at that. So you guys would click on paste. I'm doing the OK for the sake of time, and that will result, let's see here, in the analysis being run. And these are the results of our Factorial ANOVA. So we scroll up, and what we see, of course, first is the number of groups that we have, the people in these groups. We've already calculated this, of course. And yeah, we forgot one thing, I think. So let's rerun the analysis again and add just one more option. So this is also good to see. You have this history of all your analysis here, and you can just choose the same analysis again, so you don't have to go through the whole menu system again. I want to look at the options before we do this analysis. We want to test for equality of variance, and that's the homogeneity test. So if you click this one, your Levene's test will also be added to the result. Of course, it's always handy to have some descriptive statistics here. You could also add your estimated effect size and your observed power. That's the one we talked about, you remember? The post hoc power instead of the actual power. So that could also be provided by the results if you wish to. So we'll add these 2. We'll stop here. Run the same analysis again. Where did he click for the history? This one was the history. See it? Okay. So now, again, the group size, but also the means, because we ask for descriptive statistics, so you know which group means you have. And if you look at these, this is a little bit a mind bend to interpret. So you have no alcohol, no speed, no alcohol and a little bit of speed, and no alcohol and a lot of speed, and you have total. And total refers to the fact that you combine all these three. So the total refers to the mean in the no alcohol condition, disregarding the scores for speed. And you have that for a little and for a lot, and then you finally have for the totals, how much, what are the averages in the no alcohol condition, in the no speed condition, what are the averages in the a little bit of alcohol condition and a lot of alcohol, and what is the grand mean? Oh, I slipped. Well, let's go back. What is the grand mean that we have? And that's shown here. Okay. Your Levene's tests for checking the equality of variances, where these all are non-significant, so there's no difference between the variance in the for these groups.
May I ask a question?
Yes, you may.
In the field book, he says that it's more reliable to interpret the median.
Yeah.
Do you have a preference which we should interpret for the WA or exams?
I don't.
Okay,
I'll be specific when I want to have an answer on a specific number.
Okay, thank you.
Yep, you're welcome. Okay, and now finally the results for the independent factorial ANOVA. So what we see here is essentially, try to go back a little bit. Let's see. We essentially see the same results as we calculated, because we have the sums of squares for each individual independent variable, which we calculated by hand with R, for alcohol, for speed, and our interaction. And we see that our interaction, I remember this one, it was 1.9. And the other ones were the same too. So I hope that by going through these steps and by seeing which parts of the explained variance we are actually using, that when you look at a table like this, you're not like, yeah, there are numbers. I don't know what the F they mean, but it's significant. And now I hope you understand where these the sums of squares and the entire notion of explaining variance comes from, and you have a more thorough understanding of, well, what it's actually related to here.
Can I ask a question?
Sure.
What is the source named intercept? Because it has quite a large sum of squares.
Yeah, so these analysis of variance, where we dissected each and every bit of the puzzle, are actually multiple regression analysis. Just like we saw yesterday with the ANOVA, we have an intercept, we have a beta coefficient for the first dummy variable, we had a beta coefficient for the second dummy variable, etc. And this factorial ANOVA is no different. It's just a linear regression, but this time with a lot of beta coefficients and a lot of dummy variables. And one of those beta coefficients is your intercept. So the place where the line hits your y-axis when all the other variables are set to 0. So it's just one of the parts that is needed for a linear regression, which of course also has a deviation to the mean, but it's not really a relevant piece of information to explain anything of the puzzle, because we need the combination of essentially the intercept and the specific conditions that the people are in, to actually know what is the difference within this group to the total mean. So, yeah.
Which scale would this be given? Because you said like it's the intercept, so it's a value on the y-axis. But like, what is the scale? What are the units?
So the units are essentially the variance units that you would use. And well, there are a few types of these sums of squares. You have a type 2 and a type 3 error types, and I think that the most important thing is that these are not relevant for interpreting your results, for answering your research questions. So I'd love to talk about the details of this, but I think it goes too far for this course at this point. So I'll leave it at this for now. Is that okay?
Yeah. All right.
Okay. Let's see. So yeah, the one point I made earlier that I wanted to point out is that this error term that we calculated already, this 66.326, which I think we've calculated within our error term. Let's see, 66 was it again, right? Oh, we did it after we calculated the sums of squares for the model. So it would be this one, yeah, 66, and that was visually the deviation of all the actual scores to the specific group means. So all the purple vertical lines squared and added. I told you that this error term, based on the entire model, is the term that you use, is the noise that you use for each and every F test that you F calculation that you do, and you see this here in the results too. That we calculate the mean squares for the error. And based on this mean square for the error, you get the F value, this F value, by, for example, for alcohol, dividing the mean squares for alcohol by the mean squares for the error, which will land you the F value. And that same thing is done for the speed. You divide the mean squares for speed by the mean squares for the error, which will result in the signal to noise ratio, the F value. And also finally for the interaction between speed and alcohol, divide 0.477 by 0.368, which lands you this F value. This only tells you that there are differences between the main effects for speed and for alcohol. It also states, well, there's no interaction going on. So we'll look at the contrasts first, where we first asked for a Helmert contrast for the variable alcohol, and we have two contrasts that are done. One, the first is comparing the first level of alcohol, meaning the no alcohol condition, with, as it's stated here, later. And later means a level higher. So we're comparing no alcohol to the combination of a little bit of alcohol and a lot of alcohol. So we're actually making a new group and combining these two conditions and looking at that mean and seeing if that mean differs from the no alcohol condition. So it's level 1 versus the levels, all the levels later that you have. And that is a significant result. So essentially it's saying using, well, drugs in any sort, either alcohol or speed, will increase the amount of accidents. At least we have to look at the means, of course, but this is in line with our results that we put in here. The second contrast now not uses the first level anymore because it already used that chunk, puts it aside, and then it splits up the later part. like a tree structure. And then it says, well, I'm going to compare level 2 to level 3. So is there a difference between a little bit of alcohol and a lot of alcohol? And that difference is also significant. So we now know that there is a difference between a little bit of alcohol use or a lot of alcohol use within our simulator, our driving simulator. So that is for alcohol, but for speed, we didn't ask for a Helmert contrast. We said, well, we want to do a simple contrast, and we want to do a simple contrast where we use a baseline which is first. So what does this mean? Well, it means we're comparing level 2 to the first level, and we're comparing level 3 to the first level. So we're now looking at the difference between a little bit of speed use with no speed use, and that one is significant. And we are looking at the difference between a lot of speed use and no speed use, and not surprisingly, this is also significant. So this is what the difference in the two contrast types tells us. And again, if your hypothesis is something about, well, does it differ from the baseline? Well, the Helmert does not suffice because it does not give you an answer to that. We've also asked for post hoc tests if you do not have an hypothesis and just want to see where the differences are, and that is doing the multiple comparisons. We asked for the Chucky and we've asked for the Bonferroni, and it just compares each and every one to each and every level. And as you see, for our example, everything has a significant difference.
Can I ask something of the Helmert and the simple
sure,
test before?
Course.
In a normal situation, would you, for all the variables, would you use the same one? Because now what we did different one for alcohol and different one for speed, but normally would it usually be that you either use Helmert or you either use simple?
Yeah, I think that would be obvious to use the same one, but again, it depends a little bit on your hypothesis. It could be that for one of the independent variable you would have a different hypothesis than for the other one. So if that were the case, you could choose to go for a different type of contrast.
Okay, thanks.
Yeah.
Could I ask another question?
Of course.
Was there a specific reason why in this case you did Helmert for one of the variables and simple for the other one, or did you?
No, just to show you.
Okay, thank you.
Yeah. Okay.
Could you?
Yeah.
I think I got it, but could you, to make it like clear, state the hypothesis that would fit with the analysis we just did? So we would have two different ones now, right? Because we
so my hypothesis could be that would be in line with the Helmert contrast, would be drugs increases the amount of accidents, increases the amount of car accidents.
Okay.
So that would be your one hypothesis, and then your second hypothesis could be, well, speed, a high dose of alcohol increases the amount of accidents more than a low dose of alcohol. So such a hypothesis would allow you to do a Helmert contrast, because it states, well, drug use increases accidents. Well, okay, I can combine the levels and just say, well, if I use drugs, then does it differ from no drugs? Answer yes, no. And then the second part would be, well, if it's higher, then it's worse. Yeah?
Mm-hmm. Yeah.
Okay. And the other is clear, right? The simple contrast.
Yeah.
Okay, very good. Finally, and this also helps in interpreting results because, well, even if our Helmert contrast doesn't really, can sometimes not really give an answer on where the differences are exactly, if you create a chart and you add the the error bars, well, you can actually see what's going on. So if you look at this chart, which is, what kind of chart is this? Is it for the main effect or for one or the other?
A main effect of alcohol.
Does everybody agree? Is there anyone who doesn't agree?
It's for the interaction.
That's true. It's the chart for the interaction, because we're combining alcohol here with speed. And if you would only look at the main effect for alcohol, you would look at this one, where you average out on the speed levels and only look at that part. Make sense?
How would an interaction look like on a graph?
What do you think if you look at this?
Well, they would probably cross each other at one point.
Yeah, sure. So in a hypothetical, maybe a lot of a high dose of speed neutralizes all the effects of alcohol. That could be the case. It doesn't, but it could be. And in that case, a high dose of speed, this one, would neutralize the effect of alcohol. So the interaction would then be that this point would be somewhere down here, and that this point could also be somewhere down here. And then you have an obvious interaction because one condition interacts with the other. But even if you just have this middle one and you would pull it down to the bottom here, so it would go from here to there, that would also yield an interaction. So does that make sense?
Yeah, super clear. Thank you.
Yeah. So we obviously see that the effects are equal across the groups. The effects are equal across the different groups of speed and of alcohol. And it's all in the same direction, indicating that there's just no interaction going on. So the other two parts that are left are the main effect for alcohol and the main effect for speed, which you obviously see that it just increases the amount of accidents if you have more alcohol, and you see the same effect when you have more speed. We've added the error bars, so you can also see by this graph that those differences are significant, and that's what it returns to you. So just eyeballing this will give you just the same amount of information than going actually to the statistical testing, but here you make it visual, and it's always preferable to add some graphs to your paper to emphasize what's actually going on here. So going back to the slides, I think we've discussed the the contrast. Go ahead.
I might be in my head. I'm confusing and insurance. So
no, you have to put it in the chat, because I can't hear you. There's a I can't hear your voice. It's going up and down. So just put your question down in the chat and I'll look at it. So in the meantime, I'm wrapping up. We've discussed the contrasts, and we've discussed the post hoc analysis. The only thing left now is the effect size measures, well, we've discussed effect sizes earlier, where we said, well, you have a few effect size measures that indicate the effect based on the generalized results. So for example, such a R-square result actually just tells you how much variance there is explained by the model. So that is, instead of looking at the ratio of explained to unexplained variance, it's stating we're looking at the ratio of explained variance to total variance. So it's just a percentage between 0 and 100%. So that's R squared. And of course, the more variance there is explained, the better your model is. And omega squared is also an effect size that gives you just generalized a sense of what the effect size of the f value is. Actually, going into, well, no, I'll leave the details out of it. But the thing is that both these effect size measures don't give you a lot of information about what's going on. And Field also states this, that, well, what does an omega of 3 tell you? Yeah, that there's a lot of signal to noise. Yeah. So what's more relevant and what's used more frequent is that we're looking at, if you use the contrast or the post hoc analysis, you're looking at the effect size of these individual differences, of the differences between level 1 versus level 2 to determine how much of a difference there is. And this is, in general, a bit more informative than just looking at the generalized results of an f value or an R squared. And the way this is calculated is the same way as we did with the t-test. It's just squaring the t and dividing this by adding also the degrees of freedom and having the square root of that. Okay. I think that's the end for today. You're still alive?
Yeah.
Yes.
Very good. I'll be sticking around for some questions, of course. I want to wish you the best of luck with the weekly assignment, of course, and I hope you have a wonderful weekend. I hope the weather stays like this, then it will be all great.
Thank you.
Well, thank
you
all.
You too.
Thank you. Bye.
Bye.
Have a nice weekend.
You too. Bye.
Thank you so much. I really appreciate your lecture today. Like going through SPSS and like also analyzing the results was really helpful.
Very good. Thank you. Cool.
Could I just ask, whenever the p-value,
Go ahead.
whenever the p